Sir is working as an assistant professor in Civil Engineering Department, Thapar Institute of Engineering Technology, Punjab. Sir has obtained his diploma in civil engineering from Government Polytechnic Ambala and has joined his BTech in civil engineering from RIMT Institute of Engineering, Sirhind. He worked as a structural engineer in GR Infra Projects Limited and has handled the projects of pre-stressed railways overbridges, random rubble masonry, and spillway-based grouting of Koldam. In 2011, joined his ME program in Thapar Institute of Engineering and Technology and presently pursuing his PhD from the same institute. His research areas include retrofitting of structures, high performance concrete, and ultra high performance concrete. Sir, I welcome you on behalf of Civil Engineering Department, IPS Academy.
Thank you so much, ma'am.
Welcome,
so,
sir.
I will update some of the information to the participants. So it will be good for them. So I have completed my PhD in Fab 2020. All right, and now I am working in this retrofitting and rehabilitation process. We were working on the field projects also of the retrofitting and rehabilitation and design of buildings. So shall I start?
Yes, sir.
Yeah, thank you for the YPS Academy to give me the opportunity for this particular lecture. And now I welcome all the participants for this session. So in this particular lecture, we will go through with the structural, those structure element or complete structures which are distressed, right? And it means that they are existing on the ground and they are servicing to you, but due to some of the environmental actions, they are de-stressed and the durability is affected. And due to that, we need to strengthen those particular buildings, right? So in this particular lecture, we will cover some of the concepts about the strengthening, and then what are the various causes which degrade the structure. Then we will see related with these aspects, retrofitting and all these strengthening, repair, what kind of code has developed by the different countries along with the Indian context. And we will discuss some of the latest case studies which are done for the retrofitting with the latest kind of materials, right? And it shows the advancement in the field of retrofitting. And next is I will show you some of my experimental study in the laboratory which I done in the TIIT structure laboratory. So I will just give you a holistic approach before starting the rehabilitation, because your structure is basically have three different phases. Now, first is the design phases, second is the service life of structure, and third is the complete failure of structure demolished. So I will just discretize these particular three different things in three phases: design, service life, and complete failure and structural demolition. So regarding with the design, it is the choice of design engineer that how he is preparing his model, right? It is depend upon that how you are preparing your model, right, to get the design. And then second is how you are applying the loading, or in what detail you are applying the loading to the structure, because it directly depend upon the output. Next is the result interpretation, and then the exposure conditions. So if you are taking all these things appropriately in your design, right, so your structure perform in a better way, or as you expected from your structure while designing, that will perform definitely on the field. Now, if those things appropriate, then you can go for the service life of structure. Then once the structure is in service, right, once the structure is in service, it come into existence, you are using that particular structure, right? So that particular structure is subjected to so many actions, in which some of them are chemical ingress, right, extreme loading like earthquake, right, fire, sometimes it happens, corrosion, right, due to the chloride and due to the carbonation, the corrosion happens, and then some of the malicious damages, right? So this is the phase 2. Now, the performance of your structures is significantly depend upon these aspects, right? The performance of your structure is significantly depend upon these aspects. Right? So what we can do here, I will just make my screen on full mode. So here you can see that your life of structure is significantly depend upon these quality of materials which you are using at the site, then execution and supervision of the work, and periodic maintenance and repair. Sometimes it happens you designed well, you take everything good, but at the site the execution and supervision was not up to date, and because of that whatever was the expectation from the structure, that was not met. And it happens, generally it happens, right? So because of that, your rate of degradation, because of these below mentioned action of through the environment or other things, your degradation rapidly increased, right? So here in this particular phase, it is very important for the structure engineer to take care of the structures as it required, right? Now next is the complete failure structure and demolished. It is good if your structure achieved the service life, complete service life, complete design life it achieved, right? Then it is good. And then nowadays there is a sustainable construction practices and sustainable development goals are on the priority for every nation, right? So the demolition waste must be reused, it must be recycled, because there are 17 sustainable development goals developed by the UNO, and it is the duty of all the countries to follow these sustainable development goals, in which many of them, more than 70% of them, are related with the construction field, right? So it is our duty to use these materials in a beautiful way without compromising the structural property, right? Now see, if your design is not appropriate, let us say, and your minimum performance level not met, right? In that case the repair may not work, right? Repair is not at all for the structure which is constructed and having some faulty design, right? So it is already constructed but having some faulty design, it is identified later on, but at that stage repair may not work. But at this stage rehabilitation and retrofitting is applicable, right? Rehabilitation and retrofitting is applicable. Okay, so the second is service life of structure. In that stage if your quality of material, execution of work, periodic maintenance is not good, then the rate of degradation is high. In that case repair rehabilitation and retrofitting is applicable. So let's see all these three new terms, repair, rehabilitation, or restoration and retrofitting, in a beautiful way. You can see a diagram on this screen. You have on the y-axis the performance of structure, and on the x-axis you have time. So the light brown line showing the original requirement of the structure. Okay, and you have designed very well, right? The structure is constructed, but you did not apply the maintenance on that structure, right? So you ignore the repair and maintenance. So because of that, the blue line showing the rapid degradation of the performance of that existing structure. Okay, and somehow that structure met with the accident or damage. It sometimes happens, like fire, sometimes fire happens, and sometimes collision of the vehicles happen in the case of bridges or in the car parking, right? So because of that, see the black line which is coming down, it shows the accident and degradation take place because of accident, and then the performance getting lower. And you know that you do not immediately apply the retrofitting procedure. It takes some time in inspection and evaluation. So during that period of time, your performance may getting poor. And then if you apply the repair and maintenance to that structure, you will reach on the black line. Okay, you will reach on the black line. So in the black line, it shows that the performance is a bit improved as compared to the structure which is without the maintenance. Okay, so yeah, it's showing that black line at the end showing aging with maintenance and repair. Okay, so here if you this is achieved because of the maintenance and repair. If you apply restoration at this point, right, if you apply restoration at this point, okay, so you will reach at the point of original requirement of the structure. So what it means that if your structure is degraded, right, poorly, and if you want to get the original strength from the structure, right, it was as it was earlier, so you have to apply the restoration. So once you apply the restoration, you are reached at the original requirement level. Okay, and at that level, you know that there are some changes in the codal provisions has been done in the previous years. So just for the example, that zone 1 of the India is from the earthquake point of view, zone 1 is merged with the zone 2. So now the structures which are constructed earlier as a zone 1, so all the seismic forces and design was taken as a zone 1. Now it's zone 2. So the new requirement came up on that particular structure. So to improve the performance and to meet that particular demand, right, you have to retrofitting that structure. So retrofitting can meet the new requirement, even can increase the original strength of the member. So this is something, 3 points which are very important: repair, restoration, and retrofitting. Okay, now we will see some aged structure which are subjected to the service life, which are subjected to the various kinds of actions, which may be chloride, sulfate attack, carbon dioxide, okay, and shrinkage effect, alkali silica reaction, corrosion, improper construction practices, and other type of degradation. So all this we will try to cover all these aspects, because being an engineer, as a retrofitting practitioner, you have to have a skill to identify the degradation first, and then based on those degradation, you are able to apply the cure to that structure. Okay, so we will discuss one by one. This is the chloride induced corrosion map of India, in which you can see that this is you just see the blue line, which is the coastal, which is showing the coastal line of an India in the bottom, this particular map of the bottom of this map, right? And just above of that, you can see the this line which is showing the extremely severe on the right side top corner, that color showing the extremely severe. Okay, so this particular coastal line is almost 7,000 kilometers, and you know that many of the structures are constructed nearby this line. Okay, and as you move towards on the above side of the map, you will encounter with the severe corrosion, right, the area which is subjected to severe corrosion because of the chloride. And as you are moving towards upper side on the moderate, so and then you are moving towards upper side is mild, and that is the negligible. So on the top of the head of this map, there is a negligible kind of environment, which what means chloride, which affect the structure. So what you have to do, the structure which is constructed over here in the nearby extremely severe zone, you have to take care of those structures from the chloride, right? Although the carbonation takes place there, but to increase, to effectively carbonation effect, right, may occur when you have a humidity between 50 to 70%, and then you have a temperature between some range, then only carbonation will take place in this area, but chloride significantly affect. So structure constructed along the coastal line is mainly subjected to chloride induced corrosion. However, humidity in the range of 60 to 70% is favorable for carbonation induced corrosion, and always consider local effect for the structure constructed away from the coastal line. Okay, so this is all about the chloride induced corrosion in India. But it doesn't mean that if you are constructing some building in the Delhi, right, and you are ignoring the effect of corrosion, means chloride, right? Because therefore the third point says the local effect. The local effect means that if you are, say, constructing a building for the chemical factory, and that will be subjected to sulfate, right, some of the sulfate chemicals made over there, so that building more or less subjected to that sulfate attack sooner or later, right? So you have to take care of those effect also based on the occupants to construct that building. Okay, next is the service life of structure exposed to chloride. right? So that exposed to chloride means that on the y-axis you can see the damage level, on the x-axis you can see the exposure time. So in the center of that, you can see this particular member is showing the concrete member, which is having the top surface is intact with the atmosphere. So the chloride is ingress through the surface, and this red dot showing the they are transferring from top surface to this the black dot, which is showing the reinforcement, right? So this chloride, when approached to the reinforcement, and when they reached at the chloride threshold value, the corrosion will start. And you can see on the x-axis the blue line showing there is no corrosion, means corrosion free initiation phase. But once the chloride reached up to the threshold value, that there at that point, from there the propagation of the corrosion start, and then the cracks due to corrosion may take place in the member, and then you need a repair phase start from that particular points when it goes above than the maximum allowable damage level. And likewise, when for the carbonation, you say the carbonation will intact with the surface and move from the surface to the reinforcement, and when it affects the pH level of the concrete up to the threshold value, right? Before the threshold value, the structure is in the blue line range, right? In the blue line range, it is a carbonation initiation. So before that, the structure is in the corrosion free initiation phase. But once the carbonation means carbon affects the concrete pH value up to the threshold, I will tell you what is the threshold later on when we discuss the corrosion. So when it reaches to the threshold value, your corrosion will start in the structure, and at that point your cracks may take place because of the volume expansion. On the right side of the screen, you can see that on the cross section of the concrete, right, you can see the reinforcement, and this green layer is showing the passive film, right? So this passive film is basically the protective layer. We will discuss the detail in later on, but this is a kind of protective layer on the reinforcement by which your reinforcement is not corroded inside of the concrete. But once this protective layer affected because of the carbonation, right, then your corrosion will take place in the reinforcement. Now this is the image, right? So just by seeing the image, it is very difficult to understand because of what it happens, right? So it shows that there is a kind of concrete paste is completely removed, completely eroded, degraded, and then some kind of appearance is come up on the surface, and this is not a pleasant look from the structure. So lots of aggregates you can see. So it means that cement paste is completely degraded and removed from there, and it happens because of the sulfate, right? So to measure the sulfate, you have an ACI 318 building code for concrete which describes some of the different level of the sulfate, right? So if your means sulfate ions basically, you know, present in the in the groundwater, right, in the soil, in the rainwater, and if the level of those particular sulfate is keep on increasing, your effect of sulfate on the concrete structure is also keep on increased, right, is also increased, and which result in the spalling, cracking, right, degrading, and and other failure. So there are 4 types of different stages of the sulfate in which is described by the code, which is negligible, moderate, severe, very severe. So if you see less than 150 milligram per liter, it is negligible, no such effects. If you moderate, let us say in 150 to 1500 ppm. If it is severe, it is 1500 and 10,000 ppm in water, and very severe is more than 10,000 in water. And the code says you must have at least 29 MPa concrete strength to take care of the sulfate crack, right? So these are the 4 levels. Now it is very difficult to identify the cause of this particular appearance on the structure. So what is the one method? I will just tell you how you can scientifically evaluate this particular kind of degradation. You know, you can find out the reason, right, for this particular degradation. How? This is one method I just show you. This is the X-ray diffraction analysis of deteriorated concrete from Fort Peck Dam, right? So this is in the US, right? So what they did, they have found that the wall, the some area of the wall and the some area of the floor is degrade. The concrete is degraded from the top surface, and the particles get eroded from there. Other structure is very good, but some of the patches are severely affected from the sulfate attack. Okay, some of the patches are severely affected from the sulfate attack, and because of that, there is a degradation happens and it keeps on increasing. So they want to find out the reason behind that. So what they did, they took the sample from that particular wall, right? Of the sample of, well, let us say 15 gram or 20 gram is just sufficient. They just take the powder, just collect the powder sample from there, right? And they tested for the XRD, right? They did some XRD test over there, and they did some tests to find out the sulfate content in the water also, and they found that 10,000 milligram per liter, which is in the state, which is in the range of severe, right? Severe sulfate. So that stage, you know, significantly shows that sulfate is very high in that water, and it's directly intact with the concrete floor and you know, wall. So they have found that the peaks at the 2 theta, you can show that E or G, which is showing the ettringite and gypsum, and Q is a quartz, which is very less, but ettringite and gypsum are showing the peaks. So in the normal concrete, when you do the XRD, X-ray diffraction analysis, you will see the peaks of calcium silicate hydrate, calcium hydroxide, and other compound, right? But in this particular concrete sample, you found those particular minerals which are closely associated because of the sulfate attack, because of the sulfate ions, right? So it shows that your concrete is severely affected from the sulfate, and because of that, the degradation happen on this wall and on the floor. So this is one of the way how you can correlate the microstructure testing evaluation with the, you know, large scale failure of the structures, right? Now, next is the shrinkage effect. So this is one of the important things. This image shows the surface having some of the cracks which are oriented in one direction, right? And if I say how this shrinkage, plastic shrinkage happens, if your surface area of the structure is very large as compared to the cross section, at that moment of time, what happened, that the surface is exposed to the surface is exposed to the atmosphere, and the air, the atmosphere, the sun rays, right? All that stuff, if it is too heat, it is having a heat, the water start evaporating, right? The water start evaporating, and if your rate of water, evaporation of water, is too high as compared to the, you know, the rate of movement of water from the beneath of this slab to the top surface, means the bleeding of water, right? Bleeding of water happens, then on the top surface the water will not reach appropriately, right? And then top surface is getting dry, and at that point of time your shrinkage started, right? So if I see this particular thing in a close manner, you can see that kind of cracks may be seen, all right, on the slab because of the plastic shrinkage. So just see the things closely, that rate of loss of water from the surface exceeds the rate at which the bleed water is appearing. Okay, generally the depth of crack is 25 to 50 mm, and if rate of evaporation exceed 1 kg per meter square per hour, right, precautionary measures are necessary to prevent the plastic shrinkage cracking. Okay, so this is the shrinkage effect. Next is very important, is the alkali silica reaction, which takes place in the concrete structures because of the reactive silica present in the, you know, concrete, with the alkalis in the aggregates present in the alkalis, right? And then the following things may happen in the structures because of the alkali silica. The cracking may happens, expansion may happen, misalignment of the structures may happen, and spalls or pop out may happens. So if you see that the map, you know, there is a cracking formed on the surface, and it will be irregular polygons with the boundary reminiscent of the political boundaries on a map, which generally shows a map cracking. Means it shows the map of, means political map on the concrete structures, which shows the map cracking actually. Unfortunately, these three, all the three types are not specifically with the alkali silica reaction. Some of the things specifically may happen because of this, but and simultaneously might be there will be the other factors also which accelerate that kind of failure. So I will just show you one of the image of the floor, right, which is taken in from the Cape Town, and it shows that number of cracks you can see over here, and they are randomly distributed, and they are connecting with each other, right? They are connecting with each other and they are randomly distributed. So it is nothing but kind of making a random pattern on the slab, which we say is it's a map cracking. So we identify generally with this particular thing in the form of map cracking. Okay. And if I show you this particular right side image, it is taken from the Mott MacDonald test exposure site, Devon, and it is the column, the structure column you can see over here, and that column is not showing the map cracking right here. See, here is the map cracking, but here there is no map cracking. There is a vertical crack is just propagating in the direction of the stresses, right? The vertical crack is propagating in the direction of the stresses. You can see over here, right? This arrow shows over here. So now if a concrete under pre-existing stress, if the concrete is under the pre-existing stress, if there is a stress is applying on that particular structural element, then that particular structure, if affected by the alkali silica, that may not create the map cracking. That may create the cracking which is propagating towards the direction of the stresses, right? Now what they did, they cut this particular section from the structure itself, right? They removed from the section, they removed this section from there so that the stresses which are acting on that is completely removed, and they left that particular structured element somewhere else. And then they found that those vertical cracks are, instead of those cracking in the vertical direction, now the random cracking in the map direction is in the form of map is started to form. So what it mean that it's mean that if your structural element is not subject to stresses and it is affected by the alkali silica reaction, right, so that will create a map type of cracking. But if your structure, that particular structure is if subjected to stressing, that will not create the map cracking, but it create those type of cracks which are actually running along the directions, along these stresses, right? So this is something of difference between the alkali silica reaction identification, and this is the pop out, right? Pop out. So in the pop out, you can see that this particular aggregate, right? This is a white color showing the aggregate, and it just break, right? It just break. Okay, so it just break because of the alkali silica reaction. When this reaction happens, the expensive gel has formed, right, which is very close to the surface of the concrete, and that is very expensive. That create a pressure, and that pressure develops, that pressure keeps on increased and it expand, and then it pop out happens in the aggregate. Okay, so this is another image which is showing this aggregate. They have found that this is a category of charred particles and which generally having a high alkalis. So because of that, this kind of cracks may appears on the surface. So this is the alkali. Now we will see corrosion in the reinforcement. Now we will see through the basics and then we will go on the advanced. So on the lower side, you can see this is the pH scale, right? This is the pH scale which is showing the pH value from let us say 1 to 15, and your concrete is having so many compounds inside, that is calcium hydroxide, that is NaOH, that is KOH. So many compounds are there, and because of those compounds, your alkalinity of that particular concrete is very high. So if your concrete is having a high alkalinity, which is generally at about the 13, so this is the pH of the concrete pore solution. So if you measure the pH of that concrete, that may lies nearby 13, 13.5, and because of this high pH value, your reinforcement is safe inside of the concrete, right? Now if you divided these two terms, that is the acidic and alkaline. Now there's something happens in the concrete when the concrete is in the service state. When the concrete giving the service to us, during that time something is happened. Because of that, the alkalinity is reduced, and that is basically a corrosion. So the corrosion takes place when you have oxygen and electrolyte concrete, when you have chloride or a carbonation, then the mixture of that create a corrosion. If something is not there, then corrosion will not take place, but unfortunately it cannot be controlled in that way. So the presence of oxygen, electrolyte concrete and chloride or carbonation create the corrosion inside of the concrete, right? So that process actually create the corrosion, and what happens inside of the concrete, your concrete pH value is decreasing towards the acidic phase, and if it goes less than 9, the corrosion takes place, right? That starts corrosion, right? So therefore the corrosion takes place. If I just visualize this thing, so this is the reinforcement, and if it is under the high pH value, you have a protective layer of the pH. Now this is a kind of protective coating on the top of the reinforcement, right? Or when your pH value is going to decrease, this protective layer is going to diminish. Once it's going to be diminished, your reinforcement start exhibiting corrosion, right? So this is the process, basic fundamental of the corrosion. And then the cracking starts, because the cracking starts when the iron convert into the form of rust, that the volume of that bar may expand up to 6%, right? So that expansion may create the tension in the vicinity of that reinforcement, means concrete is present around the reinforcement, and that expansion create the tensile stresses, and because of that, you know that the concrete is weak in tension, and then the crack initiate. If you see the corrosion in detail, this image shows you a heavily corroded and reinforced this particular steel, and you can just see there is one steel which is completely cracked, right? Completely cracked, and it happens due to the chloride induced corrosion, right? And the second image, you can see that spalling of concrete due to carbonation and chloride ions happens, right? And it might be shows the improper construction practices also. You can see the placing of the stirrups in this particular image, right, which is not appropriate. So we need to understand these two things, pitting and this particular thing which is due to the carbonation. So in general, corrosion mostly in carbonated concrete results in early cracking and spalling of the concrete, right? And it uniformly happens, okay? But localized corrosion happens due to the chloride ions, means the chloride ingress at some particular point, and that may affect the reinforcement from one particular location, right? And then they reduce the cross-sectional area of that particular reinforcement. If you see this in a larger image, you can see this pitting corrosion in the left side image, where this particular reinforcement is severely degraded because of the pitting, and this reinforcement related with the pre-stressed wire. This is the pre-stressed tendons. So in pre-stressed tendons, this cross-sectional area loss has happened because of pitting, and you know that this particular reinforcement is always under stressed, right? It's always stressed. So once it's always stressed, the reduction in the cross-sectional area of reinforcement may result in the brittle failure of the structure. So therefore, pitting corrosion must be avoided. Now, this way we will see the fire damage to the concrete furnace supporting structure, in which you can see on the left side screen, top is the concrete furnace, under which the temperature goes around 1400 degrees Celsius, right? So in the 1400 degrees Celsius, you know that temperature is not appropriate for the concrete, right? That is not appropriate for the concrete. So when the failure has happened in this, so when the team analyzed this particular structure, and they found that there in the slab there is a degradation happened because of that high temperature, because during the process of operation, the bottom steel plate of the arc furnace was damaged locally. From some point the damage occurred, and through that damage, the liquid hot metal, which was approximately at 1400 degrees Celsius, just interact with the concrete top surface, and you know that particular temperature is not appropriate for the concrete. So they have studied this particular thing, and they have found that the spalling of the cover has happened on the bottom side of the slab. Okay, and they saw the column as well, and they found that the degradation has happened in the column phase also, right? So what they did, actually what you can do in this particular situation, right? One is the visual inspection. You can do that. You can see the damage through the visual inspection, right? And you can make your predictions, or based on experience you can make a statement that up to what extent that damage happens, right? You can see all other concrete columns are good in position, but one column is kind of degrading because of the heat. So what extent, up to what extent this concrete can damaged. But when you want to find out technically this thing with the material phase, what you can do, you can just take the sample of the different depth, right? Let us say it's the column. You can see the column. If you take the sample on the surface, then you take the sample on the 20 mm or 30 mm inside, then you can take the sample up to the depth. So those all samples can be tested through the microstructure analysis. And if you see the microstructure analysis, that crazing and spalling may, you can see you can see the cracks basically in the microstructure. So not spalling, you can see the microstructure. Through the microstructure you can see the cracks, which you can see in this image also. The cracks are just propagating through these particular aggregates and paste interface, right? Which we say is it's an interfacial transition zone, which is the weakest zone in the concrete, and the cracks may appear from there and propagated in the different directions, right? And also your aggregate is also subjected to cracking because of the heat, right? So that kind of extent of damage you can evaluate through the microstructure analysis, right? And then if you find out the performance of the concrete against the fire, right, against the heat, if you want to see the performance of the material, you must do a TGA analysis, right, thermogravimetry analysis, in which now your sample on the x-axis, you can see the temperature range from 0 to 1000 degrees Celsius. So your temperature, your material is subjected to the high temperature range, right? And then you can see, I will just show you first a minimum requirements, a general trend of the concrete against the heat. So if you see here, 100 degrees Celsius, water evaporates. Is general, right? 100 degrees Celsius, water evaporates. Now 450 degrees Celsius to 550 degrees Celsius, it is dehydroxylation of the Portlandite. Okay, so dehydroxylation of the Portlandite has happened. Now 700 degrees Celsius to 900 degrees Celsius, decarbonation of the calcium carbonate has happened. So these all phases has happened when you increase the temperature. So when your concrete subjected to fire up to 100 degrees Celsius, the water, initial water in the gel phase, in the microporous, right, in the porous, in the voids, right, pore voids, in the capillary voids, whatever water is there, that started to evaporate because of the heat. But once the temperature goes beyond that particular point and reach up around 400 to 500 degrees Celsius, right, your calcium hydroxide, whatever formed over there, that may started to degrade, right, and then cavity may form. Because of that, your bonding may decrease, your spalling may happens, that kind of things may happens. And then if it goes on increasing the temperature, you will see that the main favorable compound of the concrete, which is calcium silicate hydrate, will start to diminish, will start to consumed by the fire. So that point of time, your binding through the materials, through the semen, will start collapsing or degrading, right? And because of that, your concrete may not perform well under fire, and also it is subject to the time range also, right? So these three stages which we are discussing over here, right? And now next is the improper construction practices. If you see improper construction practices, some of the general construction practices I want to discuss with you that might be neglected at the site, but it may affect the structure severely, right? It may affect the structure severely later on, right? So this is the car parking space where the column is there, and you can see that the reinforcement is basically severely corroded, and it is corroded because it exposed to the environment and there is no cover provided to this reinforcement, right? So this something is included in the improper construction practices. Then the poor consolidation and compaction. Might be the design is well, right? Might be the concrete, might be the this reinforcement placing is well, but while concreting, your execution is not good, and because of that, this consolidation may happen, right? The next is the construction joint. So the construction joint is basically when you have too far joint, right? The joint have too far, they're having a distance, long distance, then these kind of failures may happen. So this showing the improper construction practice, which is generally we found in the structures as well. So what happens? What are the consequences of improper construction practices? Unknowingly, it reduced the design confidence. Designer was very confident about his design because it takes so much factor of safety and all the stuff, taking in a very precise way. So he is very confident, but in the construction execution, there is lots of problem regarding the improper construction, and the designer confidence unknowingly reduced. That improper construction practices reduce the durability. Improper construction practices increase the net cost of the project, right? So these all steps, right? These all things happens when you are following the improper construction practices. Now, we will discuss about the malicious damage. So this image on the left side shows the damage to a concrete column caused by the human error. Right over here, you can see that this column is completely, break at that particular height, right? It's completely break, and because of that, lots of crack are in the adjacent section also, right? So this malicious cracks is actually because of the human error. Sometimes it's found because of the human error, right? So if you closely look the surface of this crack, you will see that there is not much reinforcement is provided properly in this particular concrete section. Even we can see that if one reinforcement only over here, or might be two, but not more than that. And that is improper construction practice also. And because of this particular thing, in the yard, in the warehouses, in the storage houses, the movement of vehicle happens usually, right? And due to the negligency, if your vehicle may strike, right, may collide with this particular column, and this column is subjected to fail, is subject to degrade, or the failure happens due to the collision of the vehicle, right? So this is the zoomed image, and then if you see that both faulty maintenance and unintended human mistakes, right, such as smashing of vehicles. So this image is showing the resultant of the smashing of vehicles are very frequent causes of damage in the majority of industrial and transportation concrete structures. So wall structure caused by a truck that moved in the reverse gear and hit the gate portal by mistake, it can be seen that the absence of minimum reinforcement caused the brittle failure. Okay, so this is about the malicious damage. Now other types of degradation must be discussed over here, so that as much as we can cover, it will be good for you. So we will see the honeycombing, which is very simple at the site. Sometime we found that one because of the improper mixing, because of the improper placing, because of the improper vibration, because of the improper formwork may happen this form, because of the improper formwork it may happen if the formwork is having some not tightly packed. So the liquid which is the water which is present in the wet concrete may escape from there, and your concrete may harsh, and it gives like a honeycombing, right? If you are not applying the vibration properly, right, that may happen. Next is the medium scaling. Scaling is showing that the disintegration of all the particles with each other, so there is no bonding with each other particles, so that is the medium scaling. And on the right side corner image is showing you can see that there is a joint. Basically this is a joint, and that joint is shows as a saturation line. So the water which is interact with this particular line, the water easily penetrates through this line and goes below of this particular floor. And what will happen over here, if that particular area is in that zone where the snowfall has happened, or kind of cyclic freezing and thawing has happened, right, that particular area, the water which penetrated through this slab may convert it into the ice, right? And that ice is, you know, when water is converted into the ice, it may take the volume expansion around 9% or 10%. And during that, the tensile stresses may generate around the vicinity of that particular particle, means water or in ice. So due to that, you can see that number of cracks are appearing along the joint line, which are making generally a D type of cracking. So generally we say these are the D type of cracking. And if you do not maintain or repair this particular joint initially, then at the later stage it is converted into the severe failure kind of things. So it is severe cyclic is showing on the bottom image. If you do not, you know, take care of this kind of failure or degradation at the floor, and the degradation keep on continuing, keep on increasing, then the lower image showing the consequences of that. So you have to take care, you have to identify, actually what I am telling here, you have to you will be able to identify the cause of the crack, right? So this is a kind of assessment we are doing. So in the visual inspection, you must be able to identify the cause of cracks, that is whether due to durability point of view, whether from because of the crack, because of the loading itself. So there are so many points. So here you can see the structural cracks in bridges. So if you see the bridge on the left side, there is a crack which is propagating on this pier cap face, and it is having a 45-degree of angle, almost 45-degree of angle. So that cracks may generate because of the higher principal tensile stress, and the shear cracks may you know, propagate in that direction. But if you see on the right side, on the bottom of the pier cap, you can see that number of cracks are propagating in the vertical direction, in the vertical way, which are showing the flexural cracks right on bottom side of the pier cap. If you see the bending moment of diagram, you will see at corners of the beam, you will see at the corners there will be high shear, right? So though whatever cracks will form, they will deviate from its vertical phase, and they will deviate at 45-degree, right? And at the principal diagonal tension phase. And whatever crack in the beam occurred at the center because of the bending, that will propagate in a straight manner if they are subjected to pure bending. So this is some of the identification of the cracks through the overloading also. Now next, some of the cracks are in the building. You can see on the left side, this is the junction just below the floor level, just below the first floor level, right, or the top floor level. You can see over here, right, the reinforcement is bulging, is observed, right, and this particular form is happened in a Bhuj earthquake. During the earthquake, on the right side you can see that the failure has happened on the floor level, and there is a very poor detailing of the reinforcement has happened. So the plastic hinge has formed just above the floor. Just above the floor, the plastic hinge has formed. So this is a plastic hinge formed because the poor reinforcement and failure has happened over here. Now, the complete building may collapse, right? The complete building may collapse. So here, this is the shear failure of beam column joint under strong ground motion, right? Here, earlier it was presumed that the joint is rigid, right? The joint is rigid, but later on we based on the research, we found that there is some movement. We have to work on the joint also. But initially there was no point of confinement, right? There is no point of confinement was there. So because of the absence of confinement, the brittle failure may observed in the many buildings, right? So the one is a building which is made by the confinement, another is a made by the made without confinement. So what is happened? Failure may occur in both the cases, right? Failure may happen in both the cases, but the rate of increment of those cracks and strength degradation, right, and strength stiffness retention, all these properties depend upon the confinement level in the joint. So if it is completely absent in the joint, your rapid rate of strength and stiffness degradation may observed, and because of that your failure may happen, right? So this is the collapse, and this is because of the soft story, because of the geometrical features, your failure may happens. And in that case, you can see that the joint in the right side C image bottom, they are showing that the yellow lines, right, in the yellow points. So yellow points are the points where failure has happened and all the energy is dissipated completely, right, through those points. So it is a kind of local failure. If you see in the image of A or B, your whole building is safe, but it is failed through the bottom stories. So the bottom story is because of the soft stories, and all the energy of the building is dissipated through those points. So the local kind of failure may happens, right? We need to avoid that, because we have to design the structure in such a way that we have to utilize the complete efficiency of the building. So, but to do so, there is a philosophy that the plastic hinge should be formed in the beam rather than the column, right? In the beam portion rather than the column. So by doing so, your local failure may occur and sudden collapse may not be, may be avoided, right? And you get the large displacement at the collapse, which means that you are effectively utilizing the strength of each structural element against the extreme loading. And how to achieve these things? They said if you have the summation of the moment of column at the junction is 1.4 times greater than the moment around of that particular column in the beam, then you are getting the failure in the beam rather than the column, right? So that is given in the IS 13920 BIS 2016 code, right, which is recommended now in the codal provisions. Now, one thing is very important: when the earthquake or some other severe loading or other kind of things may affect the structure, it is not necessary that all the beam and joints and columns damaged with the same level, right? The same level of damage may happen in all the building. It is not mandatory, right? Because the extent of damage may be different in different buildings, or means in different floors, even in different columns in the same floor even. So it may happens. So when it happens, you being an engineer, when you are assessing the building, right, through the physical evaluation, right? So in that case, your understanding about the concept is very much important. So doing in that particular line, various codes have developed, right, like ACI 31, ASC 356, ACI 4113, which actually helps the various retrofitting practitioner in all over the globe and bring them on the same floor for the retrofitting practice, right? So this particular slide tells you that how these codes evolved around the world, right? So on the top row you can see evaluation, and the bottom row you can see retrofitting and new design. So if you see that retrofit evaluation is happen in FEMA 178, FEMA 310, FEMA 3103, and retrofitting and new design is happening in these three codes in the bottom one. And now we have ASC 4113, which is actually a combination of evaluation and retrofitting and design. So this is the latest development in the codal provisions, which given in one single book, right? And now we will see the 4113, what it tells. It gives you a tier 1, tier 2, tier 3. So in tier 1, it is general visual inspection, a quick identification of the potential structural deficiencies. In tier 2, the deficiency which you observed in tier 1, that will be addressed in tier 1, that will be taken care in tier 2, or detailed tier 2 can be evaluated, can be done. Tier 3, a full detail analysis, a full complete detail analysis for the building, right? And can be chosen either after a tier 1 and after tier 2, right? Or directly you can apply a tier 3. It depends upon the client, right? How much it will spend on the system. So in India, we have two codes, that is 13935 and 15988. One code is related with the masonry buildings retrofitting, seismic evaluation, repair and strengthening. One right side code showing the seismic evaluation and strengthening of existing building concrete, right? Existing reinforced concrete building. So these two codes we have. We will just look into in a brief what it said. As 13935 gives us the selection of material guidelines, techniques to be used for repair, seismic strengthening of damaged masonry buildings during earthquake, and then damageability assessment and retrofitting for upgrading the seismic resistance of existing building can be covered as per the IS 4326 and IS 13828. Now, provision of IS 13935 are applicable for building in seismic zone 3 to 5 of IS 1893 as per that. So no special requirement for building upgradation is required when they lies in the zone 2. But the important building in the zone 2 may also be considered for upgrading their seismic resistance. So these are defined in this particular code. If you go with the reinforced concrete building, that will help us to reduce the risk of death and injury because of the damaging effect, and that may produce because of the earthquake, right? And it provides a set of key steps and procedure for the assessment of the expected seismic performance of existing building, right, in the event of a design level earthquake, right? And wherever you found, you can apply a strengthening to that particular existing structure, right? We just go in brief that overview of international guidelines provided with the conditional evaluation. We have ACI 201, we have ACI 2224, 228, 364, 437, and 03736 and 1.1. So these codes are actually related with the conditional assessment, the causes and evaluation, non-destructive testing details, right? Strength evaluation for the post-tension and rapid assessment. So these are the codes. These are some of the codes which are related with the petrographic examination, CSES 1.7. AIGA is for the survey, diagnosis and repair. There are some of the RILAM report are presented over here for the industrial floor, electrochemical techniques, right? In situ concrete combined non-destructive testing. So there are some of the codes. These codes are available for the conditional evaluation. Okay. So now we have some flowchart by how we can conduct the evaluation methodology on the site. First of all, you have to do a preliminary investigation. Means you have to review the plans and relevant document related with the building which you are going to retrofit. Then you are going for the visual condition survey with documentation of deterioration and distress. And then you can go with the field and laboratory testing, right? And then even preliminary analysis and evaluation. So if it is satisfied, then okay, you can move further for the process. But if it is not satisfied, then you have to follow this process again. So if you satisfied, then you have to decide that rehabilitation is required or not. If it is required, you have to prepare the retrofitting strategy and all the documents related with that, right? And then you can issue the final report. But if it is no, then you identify a special condition to be further considered for maintenance and planning. So it is based on the engineer experience actually, based on which he can take the decision. Now, what are the different methods of retrofitting? If you see here, some of the methods which are in blue and some of the method is in red form. So some of the methods which are in blue is a passive strengthening, and some of the methods which are in red in a active strengthening. So we will see what are the passive and what are the active. Passive is basically not actively participate, right, after just retrofitting. When the load goes beyond the nominal level, then these particular methods may initiate. But the active strengthening, just after applying the strengthening, they will take care of the loadings. So if you see the passive strengthening is general wrapping of the steel plates on the bottom side of the concrete beam, right? Bottom side of the concrete beam. So when the load comes, the reinforced concrete beam can take care up to its maximum capacity. Beyond that, when the load goes beyond, your steel may take that particular load. So that's why we called it as a passive strengthening. So if you see, if the carbon plates are there, so this is simply apply on this slab, right? This is simply wrapping on this slab. So this is carbon steel plates, and here on the right side you can see that these are these steel plates which are applying over here, right? These are applying over here. This white lines which you can see over here, these are pre-stressed CFRP sheets. Now the pre-stressed CFRP sheet we have tested in our laboratory also. So this is the beam which is damaged, which we damaged actually, and then after damage we apply some retrofitting strategy. So in that we applied some retrofitting strategy. We on the right side image you can see that these three images showing the retrofitting equipment on one face, which fixed the particular FRP, right, and epoxy coated. So it is fixed over here. On the second phase we pull the FRP by some amount of force, which should be lesser than the fracture force of the CFRP, and then we paste that CFRP on that particular concrete surface, right? And then we applied the loading. On the right side you can see we are applying the loading, right? We are applying the loading. So there is a failure as happened in the FRP, right, in the form of stirrups, in the form of strips basically. And you can see that concrete surface, near surface or cover surface is just stick with the particular CFRP after failure, but the load deformation behavior is significantly improved after applying the CFRP. Now this is showing the another method of doing the CFRP, right? It is another method of showing the CFRP over here, which you can see over here, one arrangement, and in here we can see the CFRP stirrups is there. So I will just share with you a kind of video which will tell you that this particular methodology, right? Right, so you can see over here that what I wanted to explain the pre-stressing method, and the pre-stressing that was by the stirrups, and you can do it by the cables also. Here you can see on the right side of my screen that black line showing the pre-stressed cable, right? And you are applying the P force from at the both corners of the bridge, and then you have these two holes which we called it as a deviator. So if you see on the adjacent image, in the middle image, you can see the blocks at the corner which is holding the pre-stressed cable, right? These blocks are subjected to loading on the opposite direction, and the cable is just changing its plane at some point, right, and goes along with the bottom of this bridge, right, deck, and that is called a deviator block, right? So this is helpful for doing the retrofitting in case of bridges. And this is the method for saving the structure from the shear failure, right? From the both side of the pier, you're applying the block and then applying the reinforcement on the both side, and then you are giving the compression in the form of pre-stressing to that particular pier, and then your cracks maybe improve, performance of the structure may be improved, right? One thing is very important, all the these cracks must be treated before the applying the pre-stressing, right? Means epoxy grouting or something like that you have to apply in the bridges before applying the pre-stressing through the cables, right? So this is another method by which you are applying the steel plate actually. So steel plate jacketing is applying on the bottom of the bridge, right? And which increased actually the flexural stiffness EI of the beam and of the bridge, and performance may be improved. Next is the jacketing, which is a traditional method in which the section size is you have to evaluate the section size, new section size based on the demand, and compare that with the capacity, and whatever new section comes in that particular new area of that particular concrete of the section, you have to set the reinforcement and do the concreting over there. Okay. And now the recently developed material which are used in the retrofitting, which is engineered cement TDS composite, which is ECC, high performance concrete, ultra high performance concrete, and ultra high performance hybrid fiber reinforced concrete. Now we will see some case study in this. This industrial floor actually get damaged on the surface because fire brigade means vehicles are moving on this floor, so it get damaged. So what they did, this particular top core of the slab is just layered with the ultra high performance on the top with the reinforcement, right? With the reinforcement they have done, and they have give the new thickness to the floor with the ultra high performance concrete, which is having a strength of more than 100 MPa, right? So they have done in this particular crash barrier of the bridge, right? You can see over here they have applied the 30 mm thick layer of UHPC, right? So that because their UHPC is very much dense matrix, and the durability of that UHPC is extremely high as compared to normal concrete. So they have applied this UHPFRC on the top surface of this curve, right? And then they have assessed this particular performance of this particular member after some months, and they found no cracks on the surface, right? And this is the case study of Chillon Viaduct Switzerland bridge, in which the top surface of the bridge is actually retrofitted by using UHP HFRC. And it is built in 1960, and because of the alkali aggregate reaction with the induced of timing, the performance is degraded, right? So in that case, what they did, they applied the top UHP HFRC on the top surface along with the reinforcement. So means that UHP HFRC overlay with the reinforcement. You can see on over there, right? So if you see, and the new slab is laid with the 45 mm thick layer, right? In the new this particular, you can see in this image on the left side there is a reinforcement and UHP HFRC is laid on that, right? Laid on that, and then on the right side you can see the finishing of that particular slab. So total volume was 2350, and they did with the ready mixed concrete, and UHP HFRC layer was cast over the 2120 meter long viaduct, each in less than 30 working days. So they have done a wonderful job using UHP HFRC and retrofit the bridge deck. Now how it works actually. Earlier your concrete is basically having the shear resistance along the VRS. So total shear is equivalent to VRC, concrete through steel, and through there is a new component actually occurred when you are laying on the, you can see on this image on the top of this particular figure you have RUHPFRC along with the reinforcement. So means that on the top surface you laid the UHP HFRC along with the reinforcement. So there is a new resistance exists because of this material, and we added it VRU, right? VRU is the new resistance exists because of the UHP HFRC, and because of that you can see that once the crack deviate and propagate in the vertical direction, it reach propagate towards the top face of the compression face of the bridge, and you can see that the crack is deviating in the yellow color. You can see the crack deviation, the path deviated of the crack path is deviated because of the ultra high strength concrete provided in the top, right? It provides a kind of confinement to that crack. So the crack deviate itself and it reached towards on the other side. So you can say the delay in the failure, right, you will get by using this particular kind of material, right? And your shear capacity will increase. So there are some of the point, right, which I just explained you, right? Now there are actually two methods are there. One is you can do without layer of the reinforcement, and next you can do with layer on the top surface. So UHPC can be laid without reinforcement, which is generally having a thickness 25 to 40 mm, and the next one is you can use the reinforcement along with the UHPC, and the thickness is along 40 to 80 mm. So once you use the UHP HFRC with the reinforcement, the performance of the this particular material itself is very high as compared to reinforcing bars. So ultimately, your performance of the retrofitted structures is completely improved, right? And I'm just showing you regarding the code development in the UHP HFRC all over the world. There are some of the codes which have formed. First in the Swiss code, which is very detailed. In very detailed, they have explained that. Next is the ASTM. It is basically developed for the testing specimen sizes, right? What kind of specimen size should be there for testing the ultra high performance concrete. Then we have ASTHO, then we have Eurocode, then we have Canadian standard related with this particular UHP HFRC. So till date, this particular things is developed for applying this UHP HFRC in the retrofitting and for the development also, right? Next, I'm just explaining the third phase of this PPT, which show you what there is some kind of study related with the ultra high performance concrete I have done in the TIET laboratory, right? We have done that particular work to see the performance of beam column joint retrofitted with the overlay reinforcement, overlay of the reinforcement UHP HFRC. So we developed ultra high performance hybrid fiber reinforced concrete, and that particular concrete laid on the damaged area of reinforcement along with the along damaged area of concrete beam along with the reinforcement, right? So you can see on the left side there is a detailing of the reinforcement, right? Detailing of the reinforcement you can see on this side, and on the right side you can see the casting, right? In the casting, one thing I want to tell you, on the second image where the labor took the vibrator, you can see it's vertically placed, right? So the position of the vibrator is actually related to the durability part. Your vibrator should not be touched to the formwork, should not be touched to the reinforcement, right? It should be touched only concrete itself, right? So all the vibration must go inside of the concrete through the vibrator. It should not be accelerate by touching the reinforcement or by touching the formwork, right? On the third phase, we have done this curing, right? Proper reinforcement cover is provided over here to avoid the improper construction practices, and we done the curing, right? And this is the detail of the development of that beam column joint for the testing. So this is the setup we made in the laboratory to test the beam column joint, which is placed in the center, all right? And we have placed this roller supports over here, right? We have made the bolt which fixed the end, right? And then there is a jack, you can see, which is applying the axial loading to simulate the gravity loading on the column. And then we have an actuator on the top which applying the seismic force in the literal direction to the column, right, to the beam. And we can see, and the pattern of loading means the load history on that particular actuator is applied in this fashion, right? The equal magnitude of the load is having a 2 cycles, right? After 2 cycles the magnitude is increased, and then it increased, and then it increased, right? So by this way we have applied the displacement on the beam, right? And each displacement is having a 2 cycles, right? So after that testing we got this kind of hysteresis of that particular beam column joint, and you can see that lots of cracking on one phase, because the one phase is not designed as a tension phase. In the traditional way we have designed, one is a compression, one is a tension. So the tension phase performed well, but on the compression phase the tension is occurred because of the cyclic loading and it may fail, right? And lots of cracks you can see on the joint also, right? So because of that you can see the hysteresis performance on the left side of this particular beam column joint. Now what we did based on the data which we have received over here, and we decided some of the damage level to simulate the actual site condition, because on the site, I told you, all the columns may not be damaged in equal magnitude. Some of the damage may be severe, some of the damage may be complete, some of the damage may be moderate, some of the damage may be slight, right? So we create those kind of damages in our beam column joint, right? And then we chipped the beam column joint in this fashion, right? Wherever we found the cracks, we chipped those surface, right, up to the cover part. So you can see the schematic diagram on the left side, and you can see the real image on the bottom of this particular screen. Now that was the retrofitting strategy, that to simulate this particular complete damage, severe damage, moderate damage, and slight damage. We have done the complete damage we obtained, then we have severe damage, okay, to severe, and to make them severe, to get the moderate damage, we applied the loading, we get the slight damage, we applied the loading, and you can see that extent of cracks it getting reduced as we are applying the lower level of damages, right? And then we retrofitted those all damaged beam column joint using the UHP HFRC, and we lay the chicken wire mesh, right? Chicken wire mesh as a reinforcement overlay on the UHP HFRC to enhance the confinement around the joint, because there is no confined reinforcement is provided in the joint. So to simulate the confinement around the joint, we laid the UHP HFRC overlay, and the reinforcement is the chicken wire mesh. So you can see on the right side image, there are 4 steps in which we have retrofitted this beam column joint, right? So once we got the beam column joint, we retrofitted the beam column joint. You can see the performance. You can see on the top face, the performance is going to be 25 kilonewton, right? And it is approaching the 35 displacement on the x-axis, right? On the x-axis you can see the displacement, on the y-axis you can see the load, right? In between that you can see this many types of failure occurred in the UHP HFRC and the wire mesh, right? And then in the cyclic behavior, in the this is actually SED showing the severe, right? It is showing the complete damage. So this was the complete damaged specimen, and then retrofitted by UHP HFRC overlay, we achieved 25 and nearby 35 So complete damage after retrofitting again gain the strength of the original specimen, because in the original specimen, if you see here, you can see the 35 displacement over here, and here we only 10 kilonewton capacities over here. But if you see over here, you can see 35 again after complete damage, and then retrofitted, you again able to get the strength of original specimen, right? And then it was slight damage, it was severe damage, SE, so wire mesh retrofitted severe damage specimen, which shows that load capacity is increased up to 30 and the displacement capacity is increased up to 40. So it was increased, right, as compared to the previous one, when you are decreasing the damage level, initial damage level. When you have a moderate damage level, RMD retrofitted moderate damage level, and then retrofitted, you got the higher load peak capacity, which is 35 kilonewton, and get the 40 displacement over here, right? And when you see this should be RSD, so heading should be RSD, so I apologize for that. This should be RSD. So RSD showing the maximum load capacity nearby 40 kilonewton, and you have 45 displacement capacity, and you can see that the wire mesh is failed over here, somewhere over here the wire mesh is failed, and then we got the complete failure nearby 45 displacement, and the residual strength in the specimen is approximately 9 MPa, right? So this we got actually from the testing, and this is the failure pattern which you observed. You have seen that many of the cracks were initiated in the control specimen in the joint phase also. So many cracks will start from the interface of the beam and column, and then they propagate in the joint area. But here you can see that few of the cracks, means negligible kind of cracks, occurred in the joint area. So means that plastic hinges has formed on the joint itself. And as we have decided in the earlier, that the damage philosophy, retrofit, it means the design philosophy says, rather than failure of the column, the joint, the failure should occur in the beam phase to get the local damage rather than the global damage. So this particular retrofitting strategies is able to convert the global failure into the local kind of failure in the specimen which were not designed and constructed as per the latest code provision, right? On the second image, you can see that large width of the crack is observed, right? Because your fibers is able to hold the cracks even when they open in the high range, right? So there are 2 types of fibers actually. We used hooked long fiber and we used short fiber, which are crimped. So you can see over here in the third image, crimped fiber. You can see the crimped fiber in the third image, where it shows the slippage of fiber at ultimate drift. right? And you can see the crimped hooked fiber over in the second image, right? So you can see the fracture of wire mesh at higher lateral drift. Also there is a failure of the failure of the wire mesh, which actually provide the confinement, and that would be the reason of the complete failure of the specimen, right? So this is the kind of cracks which we got from the specimen. Now if you compare the ductility, you can see on the left side of the specimen where your black line is showing the controlled specimen, and as your specimen is retrofitted, now the green line is showing that it is completely damaged and then retrofitted. Red line is showing it is completely damaged, it is severely damaged and then retrofitted, and blue line is showing it is it is moderately damaged and then retrofitted, and red line is showing it is slightly damaged and then retrofitted. So as the initial damage level is reduced, your ductility performance is going to be improved, because ductility is measured from the post elastic performance, right? And in the right side image you can see the stiffness, right? In the stiffness you can see in the initial phase the stiffness is high. When you increase the drift on the x-axis, you can see the drift, on the y-axis you can see the stiffness. So on the x-axis, when the drift is increased, means the lateral deflection is increased, right? So that point of time your stiffness of the member is going to decrease. As the drift is increased, your stiffness is going to decrease, right? Your drift is increased, your stiffness is going to decrease, right? So here also you can see this particular black line is for the controlled specimen, right? And the slight damage is for the red specimen. So you can see that red damage specimen performance is very much good as compared to other type of specimens, right? And your residual stiffness is still higher than the residual stiffness of the controlled specimen, okay? And next is the strength degradation. So basically these all things are shows that how our structures behaved when earthquake initiate or interact with the structures, right? So when your drift is going to increase, you can see that the strength is decreasing, right? The strength degradation is increasing, and you can see on the left and right phase degradation, means one phase is designed for the compression phase and second is designed for the tension phase, right? And your cyclic loading is creating a tension on both the phases. So it is very important to analyze from both point of view, from the positive drift point of view, from the negative drift point of view. So you can see over here the slope of the line is going to be decreased. If you see that particular, compare the specimen and the slope of these lines, you can see the slope of this line is going to be decreased. So if the slope of the line is going to be decreased, it can bear the higher magnitude of, means it can bear the earthquake for the better way, right? By the better way. So the slope of strength reduction getting reduced as the damage level shifted from completely slight. The effectiveness of fiber and wire mesh in post elastic region resulted in lower rate of degradation in strength and helps to perform in a ductile manner. So what we need a ductility from the structures, because the structures which are designed without following the earthquake guidelines and ductile detailing, they may survive under gravity loading, but once the earthquake occurs under the lateral loading, there is a need of ductility which control the strength degradation with the increase of the magnitude of the cycle or the cyclic earthquake, right? So by that way, once your ductility is improved, means post elasticity is improved. Your concrete after first crack can lengthen the failure up to a maximum displacement, right? So it is very simple that if you can able to lengthen the path of your material after the crack, means post elasticity, in the post elasticity, if you lengthen the curve, right, you can achieve the ductility, because ultimate displacement divided by yield displacement will give you the unitless number, which is our ductility. So as much as it increased, your ductility is going to be increased, okay? Now next is the energy dissipation. So as I told you that energy dissipated in the soft story through one point, so the local failure is observed from that point only and whole building collapsed. But in the new design philosophy, if your energy is dissipated through all the points, and higher energy is dissipated, your structure is going to be improved, right? So here, if you see, the black line is showing the controlled specimen, right? And if you see, the green line is showing the retrofitted complete damaged specimen. Your next pink line, kind of this line is showing the retrofitted severe damage, and then kind of blue line is showing the retrofitted moderate damage, and then red line is showing the retrofitted slight damage. So in case of slight damage, it perform it perform excellent as compared to the other damage level. So therefore, this study says that it always depend upon the extent of damage. Your means, if you want to decide any retrofitting strategy, right, for the existing structures, first you assess the structure by visual inspection, then you evaluate the performance, and based on that particular existing damage level, you must decide the retrofitting strategy. So by doing this way, the work will be easy and it will end up in a prescribed timing, right? So this is about the today lecture, all right? And over to you, Amit.
Yes, sir. Please ask any questions if you want.
Sir, I want to ask a question.
Yeah, please.
Sir, how can we pre-assess the corrosion inside the existing concrete analytically?
Analytically,
Yes.
there is an many papers actually right now available on the internet, where they have developed the model actually, where they have developed the model to to measure the rate of corrosion, means, and to what you want to calculate, that is available up to some extent, not exactly it is there, but yes, there are some methods available in which you can see the history or the initiation of the corrosion inside of the concrete, right? So there are some testing available also, right, by which you can measure the corrosion rate.
Okay, sir.
Hello, sir.
Yes, please.
The maintenance, in the sense, the other plumbing and heat and ventilations are there.
Yeah.
Especially the plumbing, the corrosion, how it's taken place, sir?
In the building where the ventilation and corrosion, ventilation and windows are there.
Plumbing, sir, plumbing.
Plumbing are there. Then how the corrosion take place? Can you please repeat your question?
Especially water lines are corrosion happening.
Yeah.
How can you prevent it, sir?
Yeah, if there is existing corrosion is going on in a building, right, first you see the reason for that particular corrosion, right? It might be because of the chloride, it might be from the carbonation, right? If you found some kind of moisture penetration over there, right, nearby the surface, you have to stop that particular moisture penetration first, and then you can just you just repair the surface, right? You can just repair the surface. You just remove the concrete if it is damaged. If concrete surface is damaged, you can easily remove that particular surface, and you can apply the material, whatever paste is there, right? You can apply that paste as a plaster on that particular surface. It may not actually stop the corrosion, because once the corrosion is started in the concrete, I told you that alkalinity of the concrete is getting reduced. So once it going to be decreased, right, you cannot stop the corrosion, but yes, you can decrease the rate of corrosion, right? You can decrease the rate of corrosion by just applying some repairing methodology.
Any other questions? You can mail us also if you have any questions.
Yeah, you can mail me, as my mail ID I think is I shared with you in the screen, right? Or you can ask with the organizers. They can give you my email ID, and you can get my profile on the internet also, on the Thapar Institute website or on the Google, and you can ask me related to the retrofitting and evaluation. The time was short, otherwise I showed you one project which we have done for the existing building, and we retrofit that particular building. It was the industrial building, so but it was the time was short, so I'm not able to, but in future some way I will share in any workshop.
Thank you very much, sir,
Thank you,
for sharing your work with us.
thank you,
Thanks a lot, sir.
thank you,
So-
thank you very much.
So now we are ending our session, and we will meet again tomorrow at 11 a.m.